All right, as we finish section 5.5, let's talk about consumer and producer surplus. So if you remember all the way back from the beginning of the semester when we talked about supply and demand functions, we talked about an equilibrium point, x naught, p naught. Here I have graphed a supply and a demand function. The equilibrium point is their point of intersection at x naught and p naught. Economists refer to this section highlighted in blue, the area there between p naught and the supply function from 0 to x naught. They refer to that as the producer surplus. In this green part here, economists refer to as the consumer surplus. And in order to find these, we're just finding the area bounded between the graph of two functions. So if we want to find the producer surplus, we just take the integral from 0 to x naught, remember that's our equilibrium point, of p naught is our equilibrium price minus the supply function. And that's because the p naught here, this line here, is above the supply function. And that'll give us our producer surplus, and our consumer surplus is the integral from 0 to x naught of our demand function, so that's this function here, minus p naught. Okay, with that in mind, let's take a look at a quick example of consumer and producer surplus. Suppose supply and demand functions for a product are given by demand equals p equals minus 0.36x plus 9, and the supply function is p equals 0.14x plus 2, and we want to find the consumer and producer surpluses. Before we can do anything, we need to find our point of equilibrium, and we do that by setting these two functions equal to each other. So we get minus 0.36x plus 9 equals 0.14x plus 2. Moving things about and solving, we get 7 equals 0.5x. Let me make that look a little bit nice and neat. 7 equals 0.5x, so that tells us that x equals 14. And now we can plug 14 into either our demand function or our supply function. I'll pick this one at random, so we get 0.14 times 14 plus 2, that'll be 3.96. So our x naught is 14, and our p naught is 3.96. So in order to calculate consumer surplus, we take the integral from 0 to 14. That's because our x naught is 14. And again, consumer surplus is demand function minus p naught. And our demand function is minus 0.36x plus 9 minus 3.96 dx. And so that is the integral from 0 to 14 of minus 0.36x. And then we can combine these terms to get plus 5.04 dx. And now doing our integration, we get minus 0.36 over 2x squared plus 5.04x evaluated from 0 to 14. And this comes out to be 35.28. So that's our consumer surplus. As for our producer surplus, let's take a look back at producer surplus. It's the integral from 0 to x naught of p naught minus our supply function. And so that's the integral from 0 to 14, because remember x naught is 14, of our equilibrium point p naught, which is 3.96, minus our supply function, which is 0.14x plus 2. dx. And so simplifying, this becomes the integral from 0 to 14 of minus 0.14x plus 1.96 dx. And so that becomes minus 0.7x squared plus 1.96x evaluated from 0 to 14. And then that will spit out 13.72 for your producer surplus. This example reads, the projected total energy consumption C in quadrillion British thermal units per year in the United States is given by C1 equals 0.628 T plus 92.42, where 20 is less than or equal to T is less than or equal to 40, where T equals 20 corresponds to the year 2020. Determine how much energy will be saved when the actual consumption follows the model C2 equals 0.00135 T cubed minus 0.1186 T squared plus 3.62 T plus 64.91. Again, 20 is less than or equal to t is less than or equal to 40. And so this problem here boils down to finding the area between two curves. So here I've graphed the two curves. We want to find this area here. And it may seem kind of odd that area would give you just energy consumption, but it's because of the units on this graph. So as you can see here, the x-axis is year and the y-axis is consumption per year. And so because the y-axis is consumption per year and the x-axis is just that year, think about it like this. If I drew a rectangle, let's say I drew a 3 by 10 rectangle on this graph here, to find the area, we would have 3 quadrillion BTUs per year, so 3 consumption per year, times 10 years. So we have 3 quadrillion British thermal units per year times 10 years. That gives us 30 quadrillion BTUs. So that gives us 30 units of consumption. And so the area here is just 30 consumption units. And so the area on this graph is just consumption. And that's why, even though it seems weird that area could give us just a solid thing like consumption, that's why if we want to find the amount of energy saved, we just take the integral between two curves. So if we want to solve this integral, what we do is we take the integral from 20 to 40, remember because our endpoints are 20 and 40, of C1 minus C2 dt. So that's because C1 is bigger than C2, and dt because our variable is t in years. And so what that might look like is the integral from 20 to 40 of minus 0.00135 t cubed plus 0.1186 t squared minus 2.992 t plus 27.51 dt. And then that'll get us minus 0.00135 t to the fourth over 4 plus 0.1186 over 3 times t cubed minus 2.992 over 2 t squared plus 27.51 t, evaluated as t goes from 20 to 40. And then I'll just save us all some time. This is about 158.87 quadrillion British thermal units. So this new model here, this C2, saves 158 quadrillion British thermal units over this 20-year span.